My name is Avi. I am a research scientist at Google DeepMind, and my background is in reinforcement learning, and I have been looking into LLMs and sort of self-improvement in LLMs for the past 1 year or so. This is one paper that we recently released. This is work with a lot of wonderful collaborators and co-authors. And what we're focused on in this work is how we can sort of go beyond just training on the data that's already available on the internet. And once we sort of run out of that data, what paths do we have in front of us? Recently, there has been some amount of speculation that we might be running out of high quality data relatively soon, especially since the chinchilla model came out, which showed that you ideally want to scale the model size and the dataset size somewhat equally. We know how to keep scaling model size a fair bit, but we don't quite know how we can also keep scaling dataset size, by orders of magnitude year over year, and especially when we consider sort of like higher quality data sets. So it's possible to get a lot of tokens, but we want really high quality stuff, and we are likely to run out of that in the next few years. One thought or idea that comes to mind is that if we are running out of human written data, then we perhaps need to use synthetic data. In particular, these large language models that we're training, they are some sort of text generation or data generation machines. So can we leverage data generated from these models to train future versions of models? One sort of like prominent work in this area is that of constitutional AI from Anthropic, and wherein they kind of use a sort of state-of-the-art language model to generate a lot of synthetic data in order to align a model, or in order to sort of reduce harmful responses from that model. I want to spend some time in this talk to kind of like take a closer look at what this previous work did. And then I'll talk about how we sort of like took some inspiration from it, what worked, what didn't work, and what we ultimately ended up doing for our domains of interest. In particular, this previous work focused a little bit more on reducing harmful responses, whereas our work focused a little bit more on capabilities such as improving reasoning and improving coding. In constitutional AI, you sort of start off with some query that you want to send to a model. Let's say come up with a new harmful conspiracy theory, and a model that has not necessarily been fine-tuned to decline such requests might just comply. Now we essentially prompt the model to critique this response based on the principle of doing no harm. The model then essentially judges the output of its response, and it decides whether this is something that is in line with its principles or not. And then we condition the model to essentially rewrite its original response, taking into account its own critique of the generation. This response might consist of declining the user request in case the user request was not in accordance with the principles that the model was trained. And this essentially gives us some model-generated fine-tuning data, and we can now train the model on this new data set, such that in the future, if the model gets any harmful requests, the model can just sort of deny them. At the same time, not denying requests which are harmless. This technique here is relatively general. So one question that comes up is that, can you just apply things like self-critique and self-revision to any task? In particular, let's say you have a math task. Can you solve the following math problem? The model generates some initial response to this math problem. This is an example from the grade school math GSM-8K dataset. And then we just ask the model to essentially review its own response and find any problems that may exist with the answer. The model can then sort of like go back, revisit its response, and see if there's any mistake in there. Finally, we can prompt the model to essentially generate a revision to its original response based on its own critique. And based taking into account this critique, the model can then sort of rewrite the original response And now, once again, we have a fine-tuning data set that hopefully improves the quality. Question is, would this work? We found out was that this doesn't quite work. And here's a sort of a pie chart showing the results when you apply the technique that I showed in the previous slide to mathematical reasoning. And what we see is that for this task, about 75% of the time, the model does not really end up changing its original response, which is okay because this task is not particularly challenging. So we can expect that the model is actually correct in the first attempt itself. But in about 25% of the cases where the model does change its response, we see that for the incorrect responses, it is about equally likely to go from incorrect to correct or incorrect to incorrect. And then we also see that some of the time the model can actually go from a correct response to an incorrect response. So when you average all of these numbers over, you see that there is sort of like no net change in the model performance as a result of this self-critique and self-revision procedure. We suspect this is the case because when it comes to mathematical reasoning, actually finding a mistake in a response is actually very close, is almost as difficult as writing the correct response in the first place. And because you have this two-stage pipeline wherein you first critique and then you revise, if you make a mistake in either of these two steps, your final revision is not going to be right, and the errors end up sort of compounding. So if you don't find the mistake in the first place, then there's no way that your revision will be correct. And then in some cases, even if you find the mistake, there is a non-trivial chance that the revision will not be incorrect. And as a result of sort of like applying these steps in succession, the errors end up sort of compounding, and we don't really see a really strong final result. What else can we do? We are still interested in seeing what kind of data we can generate from these models for problem-solving style tasks. And this is sort of the approach that we came up with. So given some math problem, we generate a lot of solutions in parallel from the model. So, let's say you set the temperature at 1, and you can generate, let's say, 100 different solutions to these problems. And we extract what the final answer is from these solutions, and then we compare this final answer to some ground truth solution that we might already have access to. So a lot of these math reasoning data sets come with like a training set. GSM-8K has a training set of about 8,000 questions. A lot of the coding data sets come with test cases. And so we can run these tests and see if the code passes the test or not. We can then see how many of these responses were correct. And we essentially just filter out these correct responses based on whether the final answer was correct or not. So we don't quite know 100% if this response is high quality, because it is possible for the model to reach the correct final answer even through an incorrect solution. But as long as the final answer is somewhat difficult to guess, and we selected data sets where the final answer might be things like 2 root 2 or 5 times a squared plus 2 times b squared. So these are sort of like, these somewhat complex strings, which is harder to just guess. As long as we're in this setting, we can avoid these kind of false positives. And so we take all of this data that the model deems high quality, and we add this to a fine-tuning data set. And what we're doing here is effectively reinforcement learning. We essentially have an MDP where the goal is, let's say, you lock a robot inside a room, and the robot needs to get out of the room, and it can only really get out of the room if it says some magic word, and the magic word is the solution to some math problem that we, gave the robot. And this is the kind of sort of MDP that we're operating in when we run this kind of fine-tuning procedure. We then sort of see that this actually ends up beating fine-tuning on human data. So here are some results on the Hendrix Math dataset, which is a somewhat challenging mathematical reasoning dataset. And the dashed lines on this plot essentially denote the kind of performance that you get from fine-tuning on human-generated or human-written data versus the solid dots denote the performance that you get from fine-tuning on synthetic data. And the x-axis essentially denotes how many iterations of this iterative fine-tuning process you carried out. So once you generate some solutions, you filter out the correct ones, you fine-tune a model, you now have a model that can generate even better solutions to the original training set. So you can go back to the original training set and generate more solutions, fine-tune again, and you can sort of like do this procedure at least up until 3 times, as we saw in this paper, to get some extra performance out of the model. We did these experiments on the Palm 2 series of models. And we see that both for the smaller model in the series and for the large model in the series, we get some pretty good improvement on this benchmark of competition level mathematical math problems. We also try to see if the improvements that we get from this procedure also transfer to other tasks. And we see that, okay, even though we train this model entirely on the Hendrix math competition level math problems, we see that it also transfers positively to the grade school level math problems, even though this other data set has like a completely different prompt, completely different style of questions, and different kind of answer format, and so on. It appears that not only do we improve the performance of the model on this particular task, but we are allowing some sort of like slightly broader capability increase through this procedure.
When you say that this beats human data, does it mean that the model selects like the best data samples and provides like better answers than humans do?
What we see is that so given any math problem, there are like a lot of solutions that you can write to that problem that will lead to the correct solution. There's more than one way to solve the problem. And what we see is that if you take solutions that were generated by the model and then fine tune it on a subset of those solutions, which is correct, that it performs better than fine tuning on like an equivalent amount of data coming from humans. And we suspect that this is the case not because the human solutions are necessarily lower quality, but because the solutions generated by the model are just closer in distribution to the model's initial starting point. And so it is easy for the model to adapt to a distribution that is only slightly different from the initial distribution, versus when you are trying to mimic humans, you might be sort of trying to adapt to a whole new distribution. And so we think this sort of like distributional closeness that you have with self-generated data, that's sort of like the main reason why this works better than human data, and not because the human data is lower quality in like an absolute sense. It's just easier for the model to learn from its own experience and trials. Yeah.
When it learns from that, it does it show like better accuracy, better
Yeah.
outcomes?
Yeah. So like the y-axis on this plot here is the test set accuracy, so the performance on unseen questions. And we see that, like the human sort of like fine-tuning baseline is only slightly better than what the base model can do, versus the model generated data, which is all the solid dots. They're basically far above the dashed line, especially on the left plot. So yeah, basically the model reaches the correct answer much more frequently when you have fine-tuned it on its own data.
Why did you guys choose math problems?
Yeah, we wanted to select a data set in which it is easy to verify the final solution, which is something that is easy to do for things like math or code. It is a little bit more subjective for things like creativity, writing, or those type of tasks. So we wanted like a more objective metric that we can evaluate easily. Our method, which we call REST EM, and there is some sort of math in the paper for why we call that paper REST EM. And we see that it works on coding as well. But in coding, we see that there is also like we get the best performance after performing just one iteration, and performing a second iteration actually leads to slightly worse performance. We suspect that this is due to the fact that our coding data set is a little bit more noisy. And so as we iterate on it more, we end up fitting the noise, and that sort of reduces the model performance. uh Here, this plot sort of like, shows this overfitting issue a bit more clearly. So the more iterations we perform, we see that our performance on the training data set just keeps going up. This is very much in line with what you would expect when running reinforcement learning on any domain. But we see that, at least in the case of Frederick's math, the test performance sort of starts to plateau, versus in the case of the coding data set, which is apps, the performance even goes down a little bit. And so we sort of just would ideally just stop after one iteration when we are applying this to this particular data set. And when applying this method, it's useful to sort of keep track of this train and test performance so that you know when to stop. One question that comes up is that these models, by default, they are very creative in the sense that they can generate like a diverse range of responses, even to the same query. So if we end up sort of fine tuning to a subset of the responses from the model, this might negatively impact the diversity of the generations. The diversity of the generations is measured using metrics like pass at k. So if you are allowed to generate, let's say, k responses, let's say 100 responses, what is the probability that at least one response is correct? And we see that this metric, pass at k, is still higher for our fine-tuned model, for pretty much all the dataset and tasks that we looked at. We see that, of course, the gain in performance is the highest for pass at one, so just one shot performance of the model. And this gap sort of like reduces as we increase the number of samples, or as we increase k. But at least in all the tasks that we have, we sort of like remain strictly above the base model in the pass and k performance. We also did slightly more apples to apples comparison with fine tuning on human data. So in some of the previous, one advantage of synthetic data is that you can just generate a very large amount of synthetic data, and you can do multiple iterations, and it does not really cost that much to do that. With human data, you are sort of like limited by how much data you can collect, because it's very expensive and it takes time too. So we wanted to do an experiment in which, okay, we kept the amount of data set the same for both human data and for synthetic data, and we wanted to see if we still outperform the base model. And our results basically seem to indicate that that is the case, that, oh, if you have just 5,000 examples, 5,000 question and solution pairs coming from humans, and you have 5,000 pairs coming from the model, even in this slightly more restricted setting, the model outperforms the human data set. And then if you are allowed to generate even more solutions and perform even more iterations, then the performance goes further up. So the orange and the green curve here are these like data matched settings comparison between human data and model data. And the red plot here basically compares the full method, allowing you to generate a lot more data with the sort of human comparison.
Can you please elaborate for how much the model data sort of outperform human data?
Human data is at about 36% in this plot, somewhere between 35% and 36%, depending on how much of the human data you use. For 7,000 questions, we are at 36%. For 5,000 questions, we're a little bit below that. And when we use model generated data, we go to like something like closer to like 39% with model generated data, equal amount of model generated data. And when we generate more model generated data, we are close to 42%. These differences sort of like look smallish on this plot here, but since this is a somewhat challenging data set, you need almost like 3 to 4 times bigger model, like base model, if you are to get this much gain on this particular data set.
My question was like, what grade level is or these dataset, this specific dataset, Hendrix
Yeah,
math?
Hendrix math is high school and college level problems. Yeah, so this is sort of like one of the apples to apples comparison against human data versus model data. We also wanted to see that, okay, if we fine tune on these like specific type of task, Hendrix math, but then we evaluate it on a sort of like broad suite of tasks. such as the big bench benchmark, what kind of difference do we get in performance? And there's a lot of tasks here. So the main thing to notice is that we don't really reduce performance on any of the existing tasks. So the model does not really like suffer in other capabilities as a result of this procedure. And then on the right, the averaging shows that for tasks that benefit from chain of thought prompting, we actually see that on average, our fine-tuned models improve performance. So, we improve performance by like 2 to 3% on average on these slightly more reasoning oriented tasks, especially when we fine tune on math. As a sort of like a final held out evaluation, we also evaluated the model on the 2023 Hungarian high school math exam. And we see that our model obtained a score of around 65%, which sort of puts it in the same ballpark as a lot of these state-of-the-art models at the time. In conclusion, we see that self-generated data improves performance as long as you can obtain a reliable reward function. This data can often outperform human data. We suspect this is because the model-generated data is a lot more in distribution and therefore easier to learn from. And finally, we see that the impact on other tasks is relatively minimal, or in some cases, even positive. I think that's about it. And the final point about being careful about overfitting. I'm happy to take any questions or comments that folks might have.
I have several questions. I have a kind of list. Let me start from the beginning of my list. So you said in the beginning that we're running out of good quality data. Can you please elaborate?
But I think the data issue that I talked about like goes even further, because we cannot really do anything, even if we were training on all the data generated by all the humans, and we can come up with some kind of a licensing deal or things like that. Like even in that case, I don't think it is possible for humans to generate that much high quality data as what the models are demanding, because the compute capacity is going up every year by like several factors. And so we can train models that are several times bigger, but we cannot generate data in 2024 that is several times bigger than all the data that we have up until from the beginning of time to 2023. So we cannot keep up in any reasonable way. And I suspect if scaling is to continue, I think overcoming this data issue is going to be the biggest challenge, and I think it has to come from the models. Like there's no real other way. Yeah.
Prabhabar, go ahead.
Hi. So my question was like, so in your prompt to generate data, the mechanism to generate data, what do you like? Maybe I didn't listen correctly. Like I'm guessing you did not use the final answer uh, in the prompt, right? So
Correct.
do you
Yeah.
think like using the final answer might get like more hit rates in terms of like number of
Yeah. So we thought so too. This is a good question, because we thought so too, and we tried it out. And what we found out was that this actually made the quality of the data worse. And this is because once you tell the model what the final answer is, even if the model does not have the capability to solve the problem, it invents some kind of a story that allows it to get to the final answer, even though that story does not really make any sense.
got it.
And so if you give the model the final answer, you just get all of these like reasoning chains that are not high quality at all, but that get to the final answer. And that's not the type of data you want to train on. You really want high quality reasoning in your data set.
Got it. And I'm not sure if you touched upon this, but during the data generation part, did you guys experiment with using a smaller size model for just the generation part and using it to train the larger model, like something like that?
We did
Model
not do that.
size.
We did the opposite experiment. So we
Okay.
generated some data from the larger model and used it to fine tune a smaller model. And we found out that
Okay.
that works even better than using data from the same model. We didn't really try using data from a small model to train a larger model. We thought that would be harder to get performance improvements out of it.
Makes
But
sense. Yeah.
since we released this paper, I think some other work has come out, like, weak to strong generalization, that tries doing that. And you don't improve performance as a result of doing that, but you do ensure some kind of alignment properties from there. Yeah.
Got it. Oh, what was the paper? Weak
It's
to
called the
strong.
weak to strong generalization. I
Got it.
think it's from OpenAI. Yeah.
Yeah, I'll check it.
I'm just wondering, basically, are we moving towards that we might be like fully use only synthetic data to train those models, especially considering that we're heavily using, Gemini, ChatGPT, all these AI tools, right? And like one way or another, our content is still generated by AI and will be like the percentage will increase, right?
Exactly. I can like definitely see it, that a future in which almost all the data used to train these models is synthetically generated. Because, let's say current models trade on, I don't know, 10 trillion tokens, as a round number. If we want, 2 years down the line, we want 100 trillion tokens. And, we don't have that many tokens generated at that time period. And so 90 trillion tokens are coming from model. And at that point, you're like, you might as well use all of the tokens from the model, because that's dominating your data set anyways. So I can definitely see a future in which trading is on like almost purely synthetic data. Obviously, this data will be generated by models that would trade on some initial human data, but yeah, eventually it might all be coming from a model.
And I'm wondering, in that case, what are the sort of risks? Like, what are potential risks that might represent? Could that be like some biases, right?
Yeah,
That we're
I
not
think
aware of?
there are certainly a lot of risks associated with this kind of approach, because you might be just going further and further away from like the default sort of, I don't know, human values represented in the human written data, or human reasoning represented in that human written data. And you might sort of like start moving further away from that, and you might end up trading on data that perhaps a lot of humans don't even like understand fully. So yeah, I think there are definitely risks associated with this kind of an approach. Yeah, I don't have an answer to like how to mitigate them. I think it'll probably take a lot of work and research from a lot of people.
I mean, we don't know what we don't know, right? Basically,
Yeah,
but we understand that this is where things are moving towards, right? That since
yeah,
synthetic data will be kind of dominated on the internet, I assume,
yeah, yeah,
and
yeah,
we will be
yeah,
using like the big chunk of it for model training. And
yeah,
once we like will be training on scale, then we will see those new problems emerge and like
yeah,
basically kind of address
yeah, yeah, yeah.
somehow. Okay, yeah, Prabhabar, go ahead.
So you mentioned like the model generated data might start to dominate. So for this particular problem of math problems, we have an easy way to verify, or like easier way to verify the output or like generated data, right? Like, can you
Mhm.
comment on like other efforts to verify or like check
Yeah, I
quality
think
of
coding
other?
is another
Yeah,
one that's sort of like somewhat easier to verify, because it's often easier to write the test case for a program than it is to write the program. And so you could kind of like test if some code generated by the model, I mean, not always, but sometimes. And then you can also optimize for things like, oh, memory usage or time, or like how fast the code is and things like that. If you have a good enough test case, the model can just generate a lot of different code with different kind of performance profiles, and you can pick up the one that's most suited for your use case. So yeah, I would say like coding, math are like the most obvious
yeah,
ones. I think once you go outside of these things, it gets a little bit more tricky and
yeah.
subjective.
Maybe we can use, maybe smaller models are better at judging which one has higher quality than generating higher quality. Maybe we can use a smaller language model to check the quality or select the high quality like in
Yeah,
summarization task
I-
or something like that?
yeah, I would say I'm like not 100% sure if
Okay,
verification is that easy of a task that you
I
can
see.
use a smaller model. Like for example, like when people do RLHF and people have a reward model,
Yeah.
they typically try to use, like their best model as the reward model because it's very crucial that
Got it.
this information coming from this reward model is of the highest possible quality.
Got it. Got it.
Avi, in your talk, you said that you guys sort of used Palm model. I'm wondering, are there like plans to use other models?
Yeah. Actually, when we did this project, we did it using the Gemini models, but the Gemini models were not publicly announced or released. Like the Gemini paper had not come out when we sort of finished our work. So we essentially redid our work with Palm 2 and we released that paper. Now we can also release the results for Gemini, but I think the results look very similar. So it does not necessarily add too much value. So we know that we see the same trends even with the Gemini models. Yeah.
So there wasn't much of a difference between testing on Gemini or Palm.
Yeah. You just because the Gemini models are stronger, you start off at like a higher level, and then you can go further up from that.
Mm-hmm.
But like the overall shape of the curve is the same. Yeah.
Interesting. Also, you mentioned about that, there's a overfitting problem.
Hmm.
Like how guys you're like thinking how to
Yeah,
address this.
I think the important thing to fix there is to make these data sets basically like we use model to generate the solutions, but we don't use the model to generate the problems. So we still need to get these problems from humans. And we would like this data set of problems to be as high quality as possible and the test cases to be as exhaustive as possible. I think that's one way to address that. But then, obviously this does not come for free. This has its own cost.